So we're going to jump to the next topic. And the next topic is delay. Okay. So the end goal of this chapter that we might achieve by the end of the day is to create an echo effect and maybe a few recursive filters. Okay. So in signal processing, probably the most important thing that you have to do all the time is to create delay. Delay is the base of pretty much everything. And it's the base of pretty much everything because delay exists everywhere around us. As Judas said once, maybe someone said it before him, or I don't know, but we live in a world of delay. Everything is a delay in our world. So when I'm talking to you in the classroom, it takes a certain amount of time for the sound coming out of my mouth to reach you, you know, and then it takes a certain amount of time for the sound coming out of my mouth to reach the walls and to get reflected, and then a lot of complicated things happens. Okay, so most audio effects and most of the signal processing operations have to mimic that kind of behaviors that happens all the time in the real world. So delaying things on your computer on the signal processing side is extremely important. So we have to learn how to do it. Okay. So in Faust, how do we create delays? So I'm gonna clean this out a little bit. Very good. I'm gonna close that, and I'm gonna comment that out, and we're going to start over with something new. Okay. So let's say that I have an input signal, okay, and I want to delay this input signal. So add latency to it. The most basic way to do it in Faust is by using, and that's where your C++ code highlighter is not going to work. You have to use a single quote. Okay? So single quotes in Faust means one sample delay. Okay? So remember that our audio signal that we have here is a digital signal. It's a discrete signal that is stored in a buffer as a series of numbers that are samples. Okay? So here, I'm just asking my Faust code to add a one sample delay. So it's reading things with a one sample delay. Okay? So instead of being in time for reading the different samples, it's switching to the next sample and just adding a little bit of latency. Okay? So let's save that. And let's look at the diagram. There we go. I got a memory, and this memory is a one sample delay. So I'm taking an input signal, delaying it by one sample, and outputting it. Okay. So great. I'm not going to be able to do much with my sample delay, because if I try to listen to it, I'm not going to be able to hear the difference, because a one sample delay is not a lot. By the way, how long is one sample delay in seconds? It depends on the sampling rate. So how would I calculate?
Basically 1 over the sample.
Absolutely. So one sample delay is, so if my sampling rate SR is 44,100, okay, and my delay in samples is equal to 1, then the operation that I'm going to have to do is to do delay over sampling rate. So my delay that I'm adding here with my one sample delay is 1 over 44,100 seconds. It's very short. It's very, very, very short. That formula, we have to remember it because we're going to use it all the time from now on. Most of the things we're going to do in the workshop are going to use that all the time. Okay, so we really have to remember it. Who's doing that?
You. Some computer.
No. You. Okay, so here I'm introducing a delay of 1 over 44,100, which is, I don't know, I can't do that just like that. So someone has a calculator. 1 over 44. It should be very small.
0.00002.
Okay, so it's less than 1 millisecond, right? So it's very, very small. Okay. So all that to say that if at a high level I want to control delay duration as a duration, so in seconds, I'm always going to have to carry out this operation on the Faust side, right? Because depending on the sampling rate of my system, the duration might be different, right? So I really have to remember this operation here. Okay, so one sample delay. Not very, very useful for us. So if I want to add more samples, well, I could do that. But it's not very practical, especially if I want to dynamically change the number of samples, and if I want to add like 10,000 samples delay, I don't want to put 10,000 quotes, right? So there is an operator in Faust which is the at operator, and after the at operator, I can put any integer to define my delay duration. So if I say at 220, now I'm adding a 220 samples delay to my input signal. Okay, we got to be careful with the at operator, because the at operator should not have a dynamic delay length. So you can only use the at operator in Faust if your delay length is static. Okay. Why? I'm not going to tell you because it's complicated. It's a C++ issue, but if you want to have a dynamic delay length, we have to use something else that we're going to see after that. Okay, so let's say that I'm going to introduce a 1 second delay on my computer. I just need to make sure that the sampling rate on my computer is 48,000 hertz. So if I run this Faust code, now I'm adding a 1 second delay to the sound of my picked up by the microphone on my computer. I just need to make sure that the connections in jack are right. There we go. So, so 1 second.
1 second.
Okay, so it works. Very good.
Is it implemented the same even if you don't have anything in between and it's a big delay? A big delay versus a small delay?
Yeah, as long as if you use the at operator and your delay length is static, doesn't change, yes, it's the same. The reason why you can't use, well, you can't change this value here is because on the C++ side, so I'm just telling that for the people who know C++, but so there is a certain amount of memory that is allocated, right, for your delay line. And if you change the delay length, it means that you change the amount of memory that is allocated. You can't do that in real time, right? So if you want to be able to change the length of the delay line, you have to use a specific operator in Faust, which is even better than all the one that we've seen, and it's just called delay. Okay? So now delay has two arguments. Okay? Delay has two arguments. Exactly, delay is a function. That is actually, so if you want to look at it, you should look at it in music.lib. Okay. Delay takes two arguments as an input. One of them is going to be your delay length. The other one is going to be your maximum delay length. And you need the maximum delay length so that when the C++ code is created, it allocates the right amount of memory for your delay line, basically. And the maximum delay length, and that's where things starts getting a little bit weird. The maximum delay length should be a power of 2. Okay, so you really have to remember that. It's fine if it's not a power of 2. It's just that if it's not a power of 2, it's going to be less efficient, and there's going to be more chances that your code is going to crash. So you should make sure that the maximum delay length that you define is a power of 2. So let's say that here I want to create a Faust object that takes an input, adds delay to it, and I want to be able to control the length of the delay line as a duration, and I want it to be between 0 and 1 seconds. Okay? So assuming that the sampling rate on my system, on my computer, is 48 kilohertz, absolutely. It means that if I want to create a 1 second delay with my Faust object, I need to make sure that the maximum delay length as a number of samples is the next power of 2 above this number. Yeah, it's going to be 65 something. Yeah, so I need to okay.
Is there an exponential operator? Can you just change what 2 to that?
I'm not sure. That's a good question. I could do it. Well, I'm going to do it by hand here. So next power of 2. So there are very good chances that it's going to be that one. So if I do 2 power of 16, it's 65,536 samples. Okay. Absolutely. It goes 2, 15. Ah. Yeah. So if I want a 1 second delay, it's not going to be enough, right? So 2 power of 16, then I should be good. Okay. So that's going to be the first argument of our delay function. So I'm going to create a variable for that so that things are more legible, but I'm going to say max delay, and max delay is going to be that. Okay. And I'm going to put it in here. Okay. And then the next argument of my function is going to be the delay length as a number of samples. And that one can be dynamic. So I can change it in real time. It's not going to blow up. So I'm going to create a slider. And I want to use this operation because my slider is going to be So I'm going to say delay length, okay, and so that things are convenient for the user, I want the value of my slider to be a number of seconds, or a number, actually a number of milliseconds would be even more practical, right? So I'm going to say delay duration. Okay, delay duration in milliseconds. So I'm actually going to specify that. Delay duration in milliseconds. So the minimum, I'm going to say 1 millisecond. The maximum, well, actually, sorry, the default is going to be, I don't know, I'm going to say 100 milliseconds, minimum 1, and maximum 1,000 milliseconds. And I don't want to go above that, okay? And I'm going to put a step of 0.1, okay? So now I have a delay length in milliseconds, okay? And I want to convert that into a number of samples. So the first thing I need to do is to convert the milliseconds in, not yet. With this operation here, what am I doing? Yes, so I need to convert the milliseconds in seconds. So for that, I multiply by 0.001. Okay, so now, what? Exactly. So now delay length is in seconds. So it's ready to be divided by the sampling rate. Sampling rate in Faust is SR. SR is declared in music.lib. So you need to import music.lib if you want to use SR. If music.lib is not imported, SR will not work. Okay? And then there is a problem. And the problem is that this delay line here expects a number of samples, right? But it's a stupid delay line. It's stupid because it only can add delay at the sample level. Okay? So it means that the value that I'm going to send to here has to be an integer, right? So there are very good chances that the result of this operation is not going to be an integer. So I want to convert, I don't have to do it, but just to be sure, I'm going to do it. And also it's better for the people who will read your code later to see that you actually did it. So I want to convert the result of this operation, or I want to round it to the nearest integer. And for that, I'm just going to connect the result of this operation to int. Okay? So now I have a delay length as a number of sample, and it's an integer. Okay? So it's ready. I can plug it to my delay function, and I can just say delay length. Now I can save it. Faust will compile and not complain. Very good. And now I have a slider to control the delay duration in milliseconds. Okay. So if I very good. We made it. Thank you. Int is better because it will just make sure that it doesn't blow up. So
Is there any trivial way to just output an SR to the key?
Yes. Well, actually, in Faust Live, not directly. We'll see later during the workshop how to debug the signal that we're getting out of an algorithm. But the thing is, right now we didn't really make any complicated things, so it doesn't really. We'll do that later.
Okay.
So I got my delay duration in milliseconds, and I can add delay to the sound of my voice as an integer. Good. So that's fine. So now there is a problem, though. And what is the? I mean, it works. It's fine. It's good. But what is the problem? There are actually multiple problems with that. I mean, how could I improve that? No. I mean, just the delay itself.
Maybe compensate for the natural delay of the computer?
No. So actually, no. So that's fine. That's very stable. That works very well. It's a very good delay. It's very fine delay. The only problem is that it's rounded to the nearest integer, and that's a problem actually, because in some cases you might want to have a delay that is more precise than the nearest integer, right? And we'll see that there are actually cases where we want that, and it's important. For example, we'll see later that if we build a Kerr-Strong algorithm, we actually want to be able to have a delay as a decimal number and not as an integer.
How does that relate to the C++ buffers underneath, though?
Oh, then it gets more complicated, but not for you. It gets more complicated for Faust and for the Faust compiler, but for you, it's fine. So there is a way in signal processing to create a delay that is smaller than one sample by using what we call fractional delay. So in this workshop, we're not going to learn how to make a fractional delay because that's complicated. But Faust has a function for fractional delay. I'm just going to. Okay. And it's very simple. It's just f delay. Okay. So now, if I use f delay, I can give a floating point number here. So I can give a decimal number, and I can have a precise delay length, a delay length that is more precise than just one sample. So then the question you might ask is, if I can do it, why would I use delay then at all, you know? Well, there is a good reason. It's just that a fractional delay requires more memory and more computation power. Because fractional delay is actually going to create 4 delay lines. And it's going to involve a bunch of additions and a bunch of multiplications. So if you don't need a delay that is smaller than one sample, or if you don't need that level of precision, you should use delay. And you know, as a programmer, you should always think about optimizing things, right? So if you don't have to have a delay as a decimal number, you should use the delay function. Otherwise, you can use f delay.
Is this a real
Do we need to truncate to the?
No. Now we can get rid of that. And now we can have.
What type of interpolation does it use when it uses fractional delay?
So there are several implementations in Faust, but in that case, it's Lagrange interpolation. So there is a fractional delay with all-pass interpolation, which is simpler, but not as effective as Lagrange interpolation. So that one, if you say f delay just like that, it's first order Lagrange interpolation. And actually, you can control the order of the interpolation too. So to change the order of the interpolation, there are a bunch of functions for that. So f delay is first order. let me just.
Can you put the lousiest and see how much it distorts?
Yeah, just wait 1 second. So yeah, here I got first order Lagrange interpolation. If I say f delay 1, I also have first order Lagrange interpolation. It's just that f delay just points to f delay 1. If I say f delay 2, then I have second order Lagrange interpolation. If I say f delay 3, third order, fourth, etc., etc., etc. The higher you go in the order, the more memory and the more computation it involves. In most cases, first order is fine. So it will distort here anyway, because the problem is that the interpolation works as long as the signal that you provide here to control it is an interpolated signal, right? And for instance, the slider that I'm using here is not interpolated. It has steps. So even though you get floating point level precision, the slider that we have here is not giving you a lot of precision. So if I really wanted to not have any clicks when I move the slider, I would have to smooth that signal too, right? So so Daniel's question is the following actually. So let's try it. So if I compile that, if I get the audio output, do you hear that? Can you not make sound? Thank you. It's not good, right? So even though I'm doing interpolation here, I'm doing interpolation so that I can have a floating point here, right? The problem is that the output of this thing is clicking because it's just a slider. So if I don't, but even if I put a step like more precise than that, it's never going to be close enough. So
I say instead of delay length 30,000.5, instead of using the slider, just putting in it.
Yeah, that's fine.
So that we get something which is in the middle.
Yeah, no, I can totally do that. That works. And then yeah, no, that's totally fine. So no, that's I mean, like Lagrange interpolation is like very high quality. Like there is absolutely no distortion here. With all pass interpolation, you have a little bit of distortion, but with that kind of interpolation, you're totally good. So
we smooth the slider?
Absolutely. So if I don't want the whole thing to click when I move the slider, I just do the same thing that what I usually do for everything. I just use my smoothing function and say 0.999. There we go. I'm going to say f delay. Just a regular f delay. Doesn't matter. But, and so it should be fine. So it doesn't click anymore. It adds artifacts. But there is nothing that you can really do about that, because the problem is that well, it's complicated to explain at this point, but anyway, it's better. And in most cases, the other thing is that you will very, very rarely have to modify delay length by hand in real time. You know, like no one does that. The computer does it for you though, and that's what we're going to see after that. Any questions so far on delay? I mean, it's pretty straightforward. Like, so if I plot the block diagram of that in here, there we go. So I got my interpolation algorithm being displayed in here, because the only thing that I have in my algorithm is my fractional delay, and that's a first order Lagrange interpolation for fractional delay. So don't care about that. Don't think about it, because that's more complicated, and we're not going to study that during the workshop. So it's just yeah.
Can you test the smooth that you did? Mine is all 100%.
Well, that's what I said. It's going to smooth, so it's going to remove the clicks, but it's still going to add artifacts though. So it's normal. Okay. It's normal. Okay. Very good. So before we go for lunch, I don't know if we have time to do that though. You know what? Instead, so the next thing we're going to do after that is build a simple low-pass filter that we can also turn into a high-pass filter. The thing is, I don't think that we have time to do that in 20 minutes. So instead, so we'll do that when we come back from lunch. But now, instead, we're actually going to quickly look at oscillator.lib to see what's in it, because there are some very useful things in it. Okay, so if I go in the Faust source code, if I go in my Faust source code, if I go in architecture, in the architecture folder, I should have oscillator.lib right here. So I'm going to open that, and there we go. You know, for now, I'm going to try it. There we go. It's better. Okay, so oscillator.lib has a lot of things in it. Many of them are not useful at all. Some of them are very useful. So I'm only going to show you the ones that are useful in here, okay? So we have a bunch of virtual analog oscillators. So in Faust, in oscillator.lib, you know, I'm going to comment that out for now so that I can do my demo. We have a bunch of virtual analog oscillators that we can use. One that we already use is triangle. And triangle is declared in oscillator.lib. Triangle takes one argument, and it's the frequency. So if I save that, there we go. I got a triangular wave, okay? So everyone knows what a triangular wave is, right? Just bang, 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 bang. Okay. Triangle should work in most cases, because a triangle wave is not supposed to have too much aliasing. In general, because there are no really sharp edges in a triangular wave. However, if I use a square wave, that sounds different. Then a square wave is probably going to have aliasing at some point. So the implementation of the square wave oscillator in Faust is it's what we call a virtual analog oscillator. So it's not just a square wave function. Because if you just use a square wave function, as I told you yesterday, you get aliasing. And there is no other way, because the changes are very fast in the wave. And because the changes are very fast, you create very, very high frequencies. And very high frequencies get reflected at the bottom of the spectrum. And so you get aliasing. So the implementation of the square wave in Faust is not a square wave table. It's more complicated than that. So the square wave that we have in Faust is not supposed to do, well, in this current state here, it's using a complicated interpolation algorithm to make sure that there is not aliasing happening. It's not supposed to create aliasing, I think, until you go to 2000 hertz. If you go above 2000 hertz, there will probably be perceptible aliasing. So actually, we can check that. Here, I'm just going to put a slider, a frequency slider. Its default value is going to be 100, minimum value 10, maximum value, I'm going to say something very high, 8,000, and a step of 0.01. And I'm going to make sure that it doesn't click. OK. So I want to look at the spectrum of it. I mean, it's a square wave. So there are a lot of harmonics in a square wave. I don't think we're going to be able to see the earliest frequency here, but we should be able to hear them. So if I change the frequency, so the only way to hear earliest frequency is to change the frequency. Otherwise, you can't really hear it. Why? Because to be able to hear them, you have to you have to hear them move, so that your brain know where they are, basically. So if I change the frequency here in a range between like 100 hertz and 2000 hertz, there is not going to be any aliasing. So I'm going to raise the gain a little bit. So no perceptible aliasing, OK? Now I'm going to go higher. Sorry, I'm going to have to. Do you hear it? There is something in the background that is like.
You can take this all kinds of strong sidebands on.
Yeah, and you see that there are a lot of things. Yeah. I don't know if you hear it. So it's not very big, but there is aliasing. And if I was wearing headphones, I could hear that there is some kind of thing going on in the background, and that's aliasing. Those are like aliased frequency from the top that gets.
Your amplitude will be the same, because in a square wave, it's diminishing in amplitude as you go higher in the spectrum.
Yes.
And the things that alias will be at the amplitudes of the things that are
absolutely.
Over that, so they'll be pretty soft-ish.
Absolutely, but they are here, you know, and for someone who wants to build a virtual analog synthesizer on his computer, it is not acceptable to have aliasing because analog synthesizers don't have aliasing. So it's a big problem. So if I don't want to have all this aliasing, I can use a higher order interpolation. Which is going to remove aliasing at higher frequencies, and that's possible. So if I go in oscillator.lib, and if I do a search for square, so for the implementation of the square function, I need to find it. So you see that there are a lot of square function, but yeah, there we go. So square equals square n. And then 2. 2 is the order of the interpolation. So if I call this function here, which is square n, and give it a number here that is going to be the order of the interpolation, I'm going to be able to increase the order of the interpolation and get rid of aliasing for higher frequencies. There are two problems with doing that. One problem is that it's going to require more computation, which is fine. I mean, our computers are extremely powerful, and they can totally handle that, and it's not going to make any difference if you use second order or 10th order interpolation. The problem, though, is that the interpolation is going to screw up with the low frequencies. So the higher the order of the interpolation that you're using, the higher the lowest frequency that you can play is going to have to be. And I can prove you that, because here we're already doing interpolation. So we saw what happens for for high frequencies. Now I'm going to go to, you know what? I'm gonna change the range of my slider, because you guys have to be ready, because there are even chances that the whole thing blows up. So, and if it blows up, it might be loud. So, so I'm just telling you, be ready for an explosion. So, should be fine. Should be fine in theory. Okay, so. So it's not really perceptible in here, but if you listen to it in headphones, you'd hear that there is something wrong with the.
That's slowing down.
And it will be even worse if I increase the order of the interpolation. So instead of using square, I use square n, and I say order 6. There we go. Here is my square wave. It's not a square wave anymore.
You use the square waves through additive synthesis of sinusoids where you don't go above the frequency that the sampling rate will tolerate?
Because a sine wave is smooth. A sine wave doesn't have sharp changes.
Yeah, no, I mean, if you do the square wave, if you implement it through additive, adding sinusoids.
Ah, yeah, of course.
And the high sinusoid, you don't use anything that will go.
Oh, you can, absolutely, yeah. You can implement a square wave as a sum of a sine wave. That's possible. It's going to be very ineffective, though, because you're going to need a lot of sine waves. You're going to need a lot of sine oscillators. And
computing all those intermediate values.
yeah, I mean, it's fine. Your computer can probably handle it. It's just that if I run a square wave oscillator and I look at the load of my CPU, it's going to be nothing. It's I'm not even going to be able to see it. You know, if I implement my square wave with a sum of sine waves, then I'm going to see the difference, and maybe it's going to take like 30 or 35% of the processor, and I don't want that just for a simple just for a simple square wave.
Even if you do that, depending on the number of harmonics or sine wave oscillators you have, eventually as you get up there, you're still going to get aliasing.
No, because then you can. No. Absolutely, because then you can make sure that the sine wave oscillators that you're using that are at the top gets deactivated if they go above the Nyquist frequency. So
That's even more math.
yeah, but then that just like just makes things more complicated. So
Romain, if you give the first parameter a value of 0 on square n, is it equivalent to square?
I think if I do that in that case, it might really blow up. We can try. Okay, so see, with my order 6 interpolation, it is a square wave again at some point. But then there is a lot of noise in the background for lower frequencies. And then if I go to 1, it's fine. If I go to 0,
Oh, no, sorry.
You meant the order.
The order of interpolation.
You got 6 currently.
Six
He was
there.
suggesting that.
oh, if you put 0, I'm not even sure you're.
It becomes equivalent to square. Just
Or
whatever.
1.
I'm not sure. Yeah, no. You need a. So if you do that, yeah, if you do that, you need to use a different function, because that one is the interpolated square wave, and there is a square wave somewhere that is not interpolated, and well, we can look for it, but I have the same thing for a triangle. I have a triangle wave, but I also have an interpolated triangle wave to prevent aliasing. Because triangle does less aliasing than square or sawtooth, but it still does a little bit of aliasing. So in some cases, I might want to use an interpolated triangle wave. Yeah?
So does interpolation in this context mean smoothing the edges? Because it's kind of hard to understand how you go from smoothing edges to getting noise.
No, absolutely. Yeah, no. It's you basically smooth. Yeah, you just smooth the edges. It's just that that kind of interpolation creates errors. Yeah, exactly. So there is a point where you just get a lot of errors and those are like rounding errors in the floating point, basically, and at some point it just like destroys everything and it becomes noise. So yeah, so it's rounding errors in the floating point that eventually just create noise.
So I would imagine it would go above and below 1 and -1 because it's blowing up. Is there some kind of cap on there? Or?
No, well, just have to be careful.
Okay.
Well, you just have to make sure that as the person who developed the plugin or the algorithm, you should be aware of that, and you should make sure that the user is never going to be in the context where he's going to be able to do it. So you just hide it from the user, and that's why I said that it's fine to create an LFO with a sine wave and use the same function for the LFO than for a high frequency oscillator. It's not the case for a square wave, because for a square wave, if you use this square wave here to do an LFO, it's not going to work because it's going to have noise in the lower frequency. So yeah, we have triangle that does pretty much the same thing. We have sawtooth somewhere. Let me go back to the top of the library just so that we see pretty much everything. I'm just going to go very quick on that, but I'm going to stop if I see something interesting. As you see, there are a lot of implementations of different oscillators. So you should just read the library, and try them, and see which one fits your need. And you see that libraries are very well documented, because for every function, Julius wrote a small thing, where he's basically pointing you either to a page on his website or to a journal paper, like here, basically. So and then everything is very well commented, very well documented. So it's pretty good. Then, in general, in his libraries, Julius does demos versions of his objects. So that's pretty cool, because if you do the demo version of the sawtooth wave, I can just copy that and paste it in my Faust code right here, directly, straight like that in the process. Don't put any frequency, I just save. And here is the demo version of the sawtooth wave. So you see that, so we don't know how to do that yet, but we will know eventually how to do that kind of stuff. But you see that that's a fancy way of testing your sawtooth wave. So you can control the amplitude, the frequency, detuning, even kind of like portamento. You can add peak noise if you want. So you see, yeah, those are pretty nice. I think Julius's idea here was that if you want to build virtual analog synthesizer with pre-made elements that are part of the Faust libraries, you can do it. So here is your Sawtooth oscillator module that you can put in your virtual analog synthesizer if you want to build one. Okay, so Sawtooth demo. We also have pulse trains. Pulse trains are very, very similar to square waves, right? Because pulse trains are just like pa, 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 pa. So you just send impulses of only one sample. So you go from 1 to 0 straight, and you do that at a certain speed. So it's actually very close to a square wave, except that a square wave a square wave keeps the DC offset for a certain amount of time and then go back to 0, while a pulse train doesn't do that. So a pulse train really, if you plot the wave of a pulse train, it looks like that. Boom, 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 boom. A square wave doesn't look like that, because the square wave is similar to it because it has the very, very sharp edges, but it keep the DC offset for a while and then does something like that, right?
Does the pulse act like a square wave with a narrow duty cycle?
Yeah.
So it does have the negative phase as well, or is it only positive?
Well, it's taken into account in the no, but it doesn't have a negative phase though.
So it's only
So it's just
DC offset.
yeah, exactly. If you want to implement, we're not going to do that, but I'm just saying that, you know, if you want to implement a voice synthesizer, if you want to, the source of your voice is going to be in general a pulse train, because it's pretty much what your vocal folds do. You know, they just create pulses, like they're just like pop, 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 pop. And so if you want to make a voice synthesizer, you can have a pulse train and then apply filter on it to shape the spectrum of it and add formants to it. But it's a very dirty physical model of vocal fault. Okay. So, oh, look at that. Here we have a fancy virtual analog oscillator demo. So let me just try that one out of curiosity. Save, and whoa, that was big. Okay, so see, if you want to have fun later today after the workshop, you can just look at oscillator.lib and try to run the demo versions of these things, you know, and those just work right away. Parameters are already there, you don't have to do anything. Interesting. So that's probably the last thing I want to talk about this morning. Here we have a bunch of different kind of sine oscillator. The most typical way to implement a sine oscillator in C++ or in the digital world is to have what we call a wave table. So we have a wave table, and the wave table just describes the shape of a sine wave, and then it plays it at different speed, depending on the frequency that you want to achieve. Okay. All that to say that here you have sine oscillators that are based on wavetables, but there are also sine oscillators that are based on filters, and sine oscillators that are based on waveguides. And the whole idea behind that, and you guys will probably understand that more once we study filters in more details, but the idea is to create a bandpass filter with a very, 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 very narrow bandwidth, like the narrowest bandwidth that you can have, and then you send an impulse in it. And then the bandpass filter starts ringing, and that's a sine wave. And the sine wave created by this bandpass filter ringing is more pure than the sine wave created by a wavetable, because it has less numerical issues. And in terms of computation, it's actually better. So there are a lot of advantages to use sine waves that are generated by filters. So if you're implementing analog synthesizer and you wanted to have a very good sound and to not have numerical issues, you should use a sine wave that is based on a filter. And there are a bunch of them here and everything described. So oscillator.lib has that kind of sine oscillators. They are not very widely used because many DSP engineers just don't really know about them, or they know about them, but they don't really think about it. So in most softwares that you see on the market, sine oscillators are implemented as wavetables and not as filters. But there are a lot of advantages of using filters.
Is the one here that's the OSCRP, is that the one that's just calculating it directly from the unit circle, basically?
Where?
It's right there in the middle. Oops.
Here?
Yeah, down, two more, 3 lines down, 4 lines. OSCRP.
No, that one is.
It's totally impractical to calculate it that way, though.
Yeah.
But
That one.
doing the math directly.
That one here is the one that is doing it with the unit circle.
Okay.
Because
And the
you see that
complexity is-
we have an impulse. The impulse gets sent into an LFF2 and an LFF. FL is filter.lib basically. That is implicitly called in here. NLF2 is the biquad filter. I don't remember what the implementation of the biquad filter is in that case, because we'll see in filter.lib that there are like, I don't know, there are like 10 different versions of the biquad filter. I mean, there is like direct form 1, direct form 2, but then there are like a lot of shits that gravitate around that too, and those are like the poles of the filter, and so that one is doing it directly with the unit circle. Yeah, and then demo for that. We have pink noise. So you know that pink noise is it's like noise, but it's filtered, so it doesn't have a totally flat frequency response. That can be interesting to try, and yeah. All that to say that there are a lot of things in these libraries. You should just go check it out for yourself and try things out. And now with the knowledge of Faust that you have, you should totally be able to do it easily without having too many issues. Yes?
Notice that this has its own import statements in it. Are imports cumulative, like they would be in C, for instance? If I basically import music.lib, I don't have to bother.
You don't have to bother. Yeah.
Right, even though I might actually use them, because if anything in my chain imports it, it's imported.
Well, I mean, it is imported at the compiler level, but then in the C++ code, it's not. It only imports what has to be imported. So it only imports what is called in the Faust code, right?
Okay, so if I use music and oscillator,
Yeah.
the fact that oscillator brings in music will not bring music into my Faust code.
No. Yeah, that's fine.
Oh, it will.
Well, and then, I mean, the Faust compiler, I mean, Faust is just an abstraction at the top of the compiler. Like the first thing that the compiler is going to do is that it's it's going to import what it has to import. Then it's going to create a giant file where it's just going to put everything in the same file, so that there are no imports anymore. But it's only going to import what is required. And if you import something twice, well, then it doesn't matter.
Redundant,
Yeah.
that's what I'm saying. So if it's redundant, do I have to be redundant in the code level? Apparently not.
Yeah.
Which is the way C would work too.
So yeah, that's it's pretty much the idea. Okay, any questions or comments or? Okay, good.